Okay, hello, here we'll be talking about indices and logarithms. We are already on 2.3. Okay, here I'll give you what's the idea that we're going to work on. Of course, first thing, there are lots of properties and rules for indices and logarithms. If you want to study them, you can go back to the book, and also you can have my videos that I've been doing for the college algebra. So I'm going to go now directly to the application of these indices in your business study. So let's have the idea here. Okay, the output Q of any production process depends on a variety of inputs, and those inputs are known as factors of production. Okay, like land, capital, labor, blah blah blah. Okay, for simplicity, we restrict our attention to capital and labor. So we're going now to speak about capital and only labor. So we will denote the capital by K, and we're going to denote the labor by L. So the dependency of Q on K and L may be written as, so Q, the output or the product, can be a function of K and L. K is standing for capital and L is standing for the labor, which are the production function. This is called a production function, and K and L are the factors of production. Okay, let's have an example. If Q equals to what? It's a function, as you know, it's 100 K to the power of 1/3 L to the power of half. So you have the output Q equals to 100 K to the power of 1/3 L to the power of half. Then so let's say that I'm going to give you the amount of input, and K is 27 and L is what? 100. So I want to know that these inputs are going to lead to what output. So I'll plug in this K and L in the formula or in the function. Q equals to 100 K to the power of 1/3 L to the power of half, where K is 27 and L is 100. So this is going to be 100. What's 27 to the power of 1/3? It will be, of course, 3. And 100 to the power of half is 10. This means cube root, by the way, and this is a square root. 1/3. Sorry. 27 to the power of 1/3 means cubic root of 27, and you know that it's already 3. So now, if we multiply this together, we find 3000. So if you are having an input of 27 as capital and 100 as a labor, your output for this function is going to equal to 3000. Now will be the next idea. Okay, of particular interest is the effect on output when the inputs are scaled in some way. Okay, if capital and labor are both doubled, what if I doubled the capital and the labor? Does the production level also double? Does it go up by more than double, or does it go up by less than double? So if I'm going to double my inputs, I want to check if my output is also going to be doubled, or more or less than the double. So let's try. Our function was Q equals to 100. Am I right? So now, if it is doubled, we have 100, 2K, and 2L. That means my inputs are doubled. That means the capital and the labor are doubled. So I think that you already know the rules here, but let's say that, what if you don't know the rule? If you don't know the rule, 100 2 times k. What was the value of k? 27. And here 2 times L, my L was 100. Okay. So we'll have here 100 times 54 to the power of 1/3, and here 200 to the power of half. Please use your calculator here. Just first take out the cubic root of 27. I mean 54. Cubic root of 54 is 3.779. Of course, I'm not going to write it. I'll just multiply it with the square root of 200, and then I'll multiply it by this 100. So the final output was 5,345.39. So this is my new output. This is my new output after the input was doubled. So do you think that the output is also doubled, or less than the double, or more than the double? Don't forget that the first output was, let's say that this is output 2, so the first output was 3,000. So it's obvious that it's less than the double. Okay, but I don't want you to work using this method. I will show you another method starting from this step, which will make for you things more easier. Okay, once you reach this step, try to separate this 1/3. This 1/3 can do what? 2 to the power of 1/3, L to the power of 1/3, and here 2 to the power of half and L to the power of half. That means this 1/3 will be distributed to both 2 and k, and this half will be distributed to both 2 and L. Now 2 and 2 are the same bases, so you can take them alone. First I'll write so what I did here is I took the k to the power of 1/3 and the L to the power of half together, and this the numbers with the base 2, I took them alone here in a bracket together, because the same basis I can work on that. Okay, don't forget here, what did we say before? Here I'm going back to the first equation that I gave you, which is k to the power of 1/3, L to the power of half, and 100 together. I had from this 3,000, if you remember, in the first cube. So now what's left here is 2 to the power of 1/3 and 1 to the power of 2. This is going to be multiplied, just add the exponents. That means you have 2 to the power of 1/3 plus 1/2, and you'll have 2 to the power of 5/6. Okay, now using your calculator, if you multiply 2 to the power of 5/6 multiplied by this 3,000, you'll find the same result here that I got, which is 5,345.39. So I prefer, or I think that you have to use this method, because based on this method we're going to say something. Now I'll talk about the same pair, which is q equals to 100 k to the power of 1/3, L to the power of half. Now if I'm talking about this pair, I want to decide if I increased the inputs here, am I going to have the same output, or less than what I'm expecting, or more than what I'm expecting? So here I didn't decide, or I didn't tell you by what scale I'm going to increase my inputs. Maybe doubled, maybe my input will be multiplied by 10, whatever. So if this input is going to be multiplied by some scale, I want to know my expectations on the output. So instead of using numbers, just use a lambda. Let's say that lambda, lambda is the scale. Okay, lambda is the scale of increasing this firm's input. So lambda times k and lambda times L, this is my scale. So I'll do the same thing here, take the 100 and distribute this 1/3 for lambda and for k. Same thing here, lambda to the power of half and L to the power of half. Once you do this one, again collect the lambdas along, collect the lambdas together. Here you have this lambda and this lambda, take them along here, and everything else take it here. Let's k to the power of 1/3 and L to the power of half. Okay. Once you have the same base, the exponents are going to be added. That means lambda to the power of 1/3 plus half. If you add 1/3 plus half, you'll have 5 to the power of 6. So to be lambda to the power of 5 over 6. So this power is going to decide for me my expectations for the outputs. I'll give you yes, I'll give you here notes. So I found lambda to the power of 5 over 6. If this exponent 5 over 6 is less than 1, the function is said to display decreasing returns to scale. That means you will find in the output less than your expectations. If you doubled, you find less than the double. Like in the example before, in the first output I had 3,000. Once I doubled the inputs, I got less than 6,000, because you are expecting if you double the inputs, the outputs also to be doubled, but it was less than the double. So it is a decreasing return to the scale. If this exponent of lambda equals to 1, then it's a constant return to scale. That means it's what we're expecting actually. If n is greater than 1, that means, for example, if it was lambda to the power of 7 over 5, so the function is said to be increasing returns to scale. So whenever you want to decide, look at the power or the exponent of lambda. Okay, I'll give you a question, but I want you to try it by yourself. And let's So let's say that q equals to 2, k to the power of 1/3, L to the power of 2 over 3, and to determine if it will have increasing, constant, or decreasing returns to scale, please here use lambda. Don't substitute any numbers, just put lambda with the k and lambda with the L and decide what will be the exponent of the lambda to help you for this exercise. If you have any question, ask me please.